welcome back to my channel. Click on the link in the description box to get a worksheet which goes along with this lesson. In this lesson we're going to have a look at the atomic structure topic of advanced higher. Atomic structure advanced higher focuses on refining your understanding of electrons and their placement within the atom. At the moment you would probably draw an atom which looked something like this, with protons and neutrons in the centre, and then electrons around the outside. This is not incorrect, however, the placement of the electrons can be refined. First of all, we'll look at some reasons behind why we can do this. The first reason is wave-particle duality. So electrons can act as the particle that you're familiar with, however they can also act as a wave. This is known as wave-particle duality. Because of this, it allows us to define orbitals for the electrons. These are mathematical representations called wave functions, and they tell us where electrons can be found 90% of the time. Each orbital can hold a maximum of 2 electrons. Previously you'd worked on the 2-8-8 rule, and again this isn't incorrect, but we can make it more correct. So each of the orbitals have different names and shapes. Let's have a look at them in turn. S orbitals are spheres. So in the first shell we have an S orbital, in the second shell we have an S orbital and it's bigger, and in the third shell we have an S orbital and it's bigger. Right, they are just spheres. Once we move up to the second shell, we also have p orbitals. Now p orbitals have this sort of shape, kind of like a dumbbell. There are 3 p orbitals, X, Y and Z. You can be asked to either identify or draw them, and all you need to do is put in some axes to show which is which. So for example, if we label that axis X, that's a px orbital. If you were to label it Y, then it would be a py orbital. So they exist perpendicular to each other. It's quite hard to draw the third one in, but it goes something like that. So these happen from shell 2 upwards. And then once we get to shell 3, we have the d orbitals. So there are 5 different d orbitals. So the first one that we'll look at is in between the axes. So we've got X and Y here. And they look sort of like 2 p orbitals joined together. If we change the labels on our axes to be Z and Y, this would be dyz. And if we change them again to be X and Z, then this would be dxz. Again, these are all superimposed on top of each other at perpendicular angles to each other. We then have 2 orbitals which lie along the axes themselves. So if they are on the X and Y axes, here, dx squared minus y squared, and then the one on the Z axis looks very different, and you need to remember this one. So it looks like a p orbital with a donut around the middle. This is the dz squared. Very distinctive shape for this one that you need to learn. There are 7 f orbitals, and they've got much more complicated shapes, and you don't need to know those. You just need to know that they do exist. So each electron in an atom has a unique address, which is represented by 4 quantum numbers. So if you think of your address at home, you have your name, you've got the number of your house, you've got your street name, you've got the town you live in, and then you've got your postcode. So different parts which identify who that letter is going to in your house. And no 2 people in the house can have the exact same address because the people in the house have different names. So here, all of your electrons have to have 4 different quantum numbers, and no 2 electrons can have the same 4 quantum numbers. One of their quantum numbers has to be different. So let's look at what the quantum numbers actually are. So each of the quantum numbers has a name. The first one is called the principal quantum number. You are used to the principal quantum number. This is the energy shell, and you have been dealing with these since S3 National 5. So this is your main energy level. Okay, so think of that like the big circle you used to draw before you drew in electrons. and it's given the letter N, and it has possible values of 1, 2, 3, etc. Quite straightforward. The next one is the angular quantum number. So this gives you the shape of the orbital. So we've just had a look at those shapes. And this is given the letter L, and it can go from 0 to n minus 1. So if your n is 2, then this can have the value of 0 or 1. If your n is 3, then it can go 0, 1, 2. You've then got your magnetic quantum number. Okay, and this gives you your orientation. So as I said, for P and D, they can lie along the different axes, and this is given the letter ML, and it can go from minus L to positive L. And then finally you have your spin, and this is the direction of spin of your electron. So electrons can spin up or they can spin down. And this is given the letters MS, and it can only have two values, +0.5 or -0.5. So spin up, spin down. So let's recap from National 5 and higher just before we take this on any further. So you have your 288 rule. You also have that electrons fill singly before pairing. Now, that still stands. We're just going to refine it slightly. So if I was to draw nitrogen, you would draw an N and you put a circle. You'd say in the first shell we'd have 2 electrons. And in the second shell, you'd say we've got 5. And we'd go 1, 2, 3, 4, and then we'd start pairing up. Okay. Now, we're just going to make this that it's not just one big circle that they're in. Okay, they're in orbitals, so we won't actually draw them out. We're going to use different notations to help us. So at advanced higher level, we're going to represent them more accurately using orbital box or spectroscopic notations, but there are some rules to learn before we can do this. The first rule is the Aufbau principle. So in the Aufbau principle, electrons will fill in order of increasing energy. So the first orbital we have is the 1s. Then we've got the 2s and the 2p. Then the 3s and the 3p. And then this is where it gets a bit strange, because we're going to have the 4s next and then the 3d. Now this is to do with the shape of the orbitals and how close they can get to the nucleus. Just remember, this is the order that they go in. Okay, so they go up in the normal steps, and then we have 4s before the 3d. Then we have Hund's rule. So electrons are going to fill degenerate orbitals. So degenerate means that they have the same energy, and they'll do this before they pair up. So they'll fill each of the 3p's singly before they pair. Okay, so for example, if you've got your 3p orbitals, they'll do this rather than doing that. Okay, so they'll fill individual boxes until they're all full with one electron before they start pairing. Then we have the Pauli exclusion principle. So this says that no 2 electrons can have the same 4 quantum numbers. In practice, what this means is that if they pair up, they have to have opposite spins. And this is because once they're in the same box, then they have their other 3 quantum numbers are identical, so they need to have their 4th one be different. So one needs to spin up and one needs to spin down. So let's have a look at how we would now write out electron arrangements. So carbon, if we just start with the normal electron arrangement, which you would get from the data book, is 2, 4. So this is your first shell, and this is your second shell. And we're just going to make it a little bit more refined now. So in the first shell, we've got 1s. We've got 2 electrons, so they're going to pair. One's going to go up, one's going to go down, and we write that 1s and then a 2. In the second shell, you've got 2s, and then you've got 2p, but you've got 3 2p's. Okay, so you've got px, py, pz. And we need to put 4 electrons in. So we fill up this 2s box first, so we've got 2 in there, and then we've only got 2 electrons left. So they're going to go into the 2p, and they're going to go in parallel before they would start pairing. Let's look at a bigger atom. So let's look at chlorine. Let's look at a bigger atom, look at chlorine. So we've got 2, 8, 7. So here we're going to have our first box for our first shell, so that's 1s. You've got the 2 electrons going in there, so 1s2. And then we've got our second shell. So you've got your 2s and the 2p, and we've got 8 electrons to put in. So the first 2 go into the 2s, 2s2, and then we've got 6 to put into the 2p, and that gives us the 8 electrons from the second shell. And then your third shell, you've got your 3s and 3p. So we've got 1, 2 to go in here. That leaves us 5 to put in. So we're going to go 1, 2, 3, 4, 5. So we've got 1 that is unpaired. So this top row is your orbital box notation, and this bottom row is the spectroscopic notation. Pause the video now and write the orbital box and spectroscopic notation for each of these elements. So lithium has 2, 1. So we're going to have 1s2 and 2s1. Aluminium is 283. So you've got 1s2, 2s2, 2p6, 3s2, and 3p1. For neon, we have 2, 8. So 1s2, 2s2, and then 2p6. So that shell is full. And then iron, we have 2, 8, 14, and 2. So 1s2, 2s2, 2p6. We're then going to start filling the third shell, so we've got 3s2, 3p6. Now remember the 4s will fill first, so I'm going to join that one in just now. So we've got 4s2, which is that shell. And then we have a look at these two. So we've taken up 8 of the electrons, so we've still got 6 for the 3D. So I'm going to draw that under here because I don't have enough space at the side. There are 5 shells in the 3D. Okay, and we've got 6 electrons that we need to put in. So we're going to go 1, 2, 3, 4, 5, and then put the 6th one in there. So 3d6. Let's look now at identifying quantum numbers. Now we're going to do something you'd probably never be asked to do, which is to write out a quantum number for every single electron. And this is just so you can see how these addresses work. So if we say that we've got carbon and it's got 6 electrons, so I'm just going to number the electrons. Imagine we're going from the nearest nucleus out. So our first electron is going to be in shell 1, and then L goes from 0 up to n-1, so for this is going to be 0. And then ML goes from negative L to positive L, so 0. And then MS can be plus a half or minus a half, so we start with plus a half. So the second one that goes in there is also going to be 1, 0, 0, and it has to be negative a half because it's got to be the opposite. Now if we go into the next shell, we're we're going to have 2, and we're starting with the s, so it's going to be 0 and 0, and you're going to have plus a half, and then your other electron in that s orbital is going to be the minus a half. We're then looking at the next one, so we're still in the main shell, which is 2, and the L goes from 0 to n minus 1, which is going to be 1, so it's going to be 1 in there, and then ML goes from minus L to positive L, so we're going to have minus 1, and we're going to have positive a half, and then the next one's going to be into the 0, because we're going into the next one along, we're not going into the same one, and it's going to have the same spin as the other one, because they're both in the P's, and they're both going to spin up. So try and do the same thing for fluorine. Okay, first of all, we're going to number the electrons. And this is just so we can think of them going from the inside to the outside. So the first one is going to be in n-1, L0, ML0, and we're going to have plus a half. The other one is also going to be in that 1s shell, but it's going to have the opposite spin. Moving into the second shell now, and we're in the S, so it's going to be 0, your ML is 0, you're going to have plus a half, and then you've got the other electron also in the 2s, and it's going to be minus a half. We're still in the second shell, but now we're moving into the P, so that is L1, and we've got the option of minus L to positive L, so minus 1, and we're going to start with the spin ups, and remember you're going to have 3 of them. Okay, so they're going to go in there spinning up before anything goes in and spins down. So you've got those 3 spin up electrons, and now we're going to go back in and we're going to pair them up. Now, the most I've seen that you've ever had to do is just to name what they could be, or say what the 4th quantum number could be for a particular electron. So you just need to try and remember what these numbers match up with. So here, this is the number at the start, okay, that's that number there. And then this bit here, your S's and your P's, okay, so if it's 0, that means S, and if it's 1, that means P. Okay, and then you're going into this part here, so this is just the orientation in space. The sphere can only be orientated one way, and this roughly equates to your x, y, z, but not quite. There's no -1 is x, 0 is y, or whatever. It's just that we've got 3 different possible orientations, and then you've got your spins up or down. So the periodic table can be split into 4 sections according to the last orbital that the electron goes into. So if you're in this section here, the last orbital that an electron goes into is the S. If you're in this section here, the last one is a P. If you're in this bit, the last one's a D. And this bit, the last one's an F. So what block of the periodic table would an ion with a 3+ charge and 60 electrons be found in? So if your ion has a 3+ charge and it has 60 electrons, that means that your element had 63 electrons. If you look at the periodic table to find the element with 63 electrons, you'll find that that's europium, which is in the F block. Quite a common multiple choice question to have something like that. So linking the periodic table to the electron arrangements, we can have a look at ionization energy. So there is a special stability associated with full or half full subshells, and this can lead to anomalous ionization energies because of the stability of the electron arrangement. So if we have a look at nitrogen and oxygen, so if you have a look at the nitrogen electron configuration, so if we compare nitrogen and oxygen, so nitrogen's electron configuration is 1s2, 2s2, 2p3, and it has an ionization energy of 1402, whereas oxygen is 1s2, 2s2, 2p4 with an ionization energy of 1314. Going from left to right across the period, the ionization energy should increase due to increasing nuclear charge. However, nitrogen is anomalously high, so it's higher than oxygen when it should be lower, because it has a half full subshell. Okay, so it has your 3p electrons like this, and this is more stable than oxygen. So oxygen looks like this, and this is less stable. So there's a stability with the half-full p subshell. Let's have a look now at shape. So VSEPR theory, which is valence shell electron pair repulsion theory, allows us to predict the shape of molecules or polyatomic ions. So there are some rules for doing these calculations. They're very straightforward. So you count the number of electrons on the central atom, so that's in the outer shell, just as you would have when you tried to draw like dot and cross pictures in the past. Add on the number of atoms that are bonded, take away any charge, divide what you're left with by 2, and that tells you how many electron pairs you have, and then take away the number of atoms bonded to find out how many non-bonding pairs you have. That's the easy bit. Once you've got those numbers, you then need to work out what shape you would have. You need to be able to state the shape of the electron pairs and the overall shape of the molecule, which is influenced by the non-bonding pairs. So let's first of all just look at electron pairs. So if you have 2 electron pairs, the shape would be linear. Okay, so this would be something like this here. Okay, just in a straight line. If you've got 3 electron pairs, this would be trigonal planar, so like a triangle, just completely flat. If you have 4, you should be used to this one, it's tetrahedral. So there's a bit more shape involved in this one, a little bit harder to draw. Okay, you can also have it with the wedges and dashes. Okay, so you can see the shape there. If you have 5, we call this trigonal bipyramidal. So this one, much easier to draw with the wedges and dashes. So I'm going to draw some straight lines. And then you've got one going back and one coming forward in the middle there. And then for 6, you have octahedral. Now this seems weird, but it's because of the shape that this would make. If it was an actual 3D shape, it would be 8-sided. Okay, so if you were to draw in all of the lines here for the planes, it would be the shape you would get, would be an octahedron. So that's your octahedral shape. If you're using the wedges and dashes, as long as you have an equal number of wedges and dashes, you'll be correct. Okay, so don't be too concerned as to where they are. So the shape of the molecule is determined both by the number of electron pairs that are around the central atom and how many of those are non-bonding pairs. So electron pairs will always try and repel to be as far apart as they can, but your repulsion depends on the type of electron pair that is repelling each other. So if you have 2 pairs of non-bonding pairs, they have the most repulsion. They are going to try and get as far apart as possible. If you have a non-bonding and a bonding pair, they're going to try and get as far apart as they can, and then bonding and bonding pairs have the least repulsion. So if you have a mixture of this going on in a molecule, then you need to consider where things will go to try and get your non-bonding pairs as far away from each other as they can be. So here, if we had 2 electron pairs and you have no non-bonding pairs, then this is just going to be linear. So this would be something like this here. So just a straight line. If you have 3 electron pairs and no non-bonding pairs, this will be trigonal planar. So just flat, okay, with the 3 things coming out. If you have 4 and no non-bonding pairs, that would be tetrahedral, so that would be like methane or anything else from group 4. It's a very classic shape. And if you've got 5 with no non-bonding pairs, that would be trigonal bipyramidal. So far, the same as what we've just looked at. The difficulty comes in when we start looking at having bonding pairs as well. If you've got 6, then it's going to be octahedral. Let's start introducing some non-bonding pairs. So if you have 4 electron pairs in total, but 2 of them are non-bonding, this is going to be angular. So this is what happens when you have water. So your two non-bonding pairs, the two non-bonding pairs are going to get as far away as possible. So overall the shape will be tetrahedral, but the actual molecule itself, if you cover up these two, has this angular shape. If you have 4 and you've got one non-bonding pair, then this will be trigonal pyramidal, so just a single pyramid. And this is what happens when you have ammonia. So you'll have your 3 bonding pairs will push down the way, and your non-bonding pair will be on the top, taking up as much space as it can. So overall tetrahedral, but if you ignore the non-bonding pair, the molecule itself is trigonal pyramidal. If you have 5 electron pairs and 2 of them are non-bonding, those 2 non-bonding are going to get as far away as they can. So your molecule itself is going to be trigonal planar, so flat, and your 2 non-bonding pairs are going to go at 180 degrees from each other. And then finally, if you have 6 in total but 2 are non-bonding, then you're going to get square planar. So a similar situation as to the one we just looked at, but we've got 4 around the middle, and then the 2 non-bonding pairs at 180 degrees from each other, so as far apart as they can possibly get. Let's have a look at some examples. So here we have NH3. Nitrogen has 5 electrons. We're going to add 3. We've got no charge, so total is 8. Divide that by 2, we've got 4 electron pairs. So the shape of the electron pairs would be tetrahedral. And then I'm going to take off the 3 things that are attached, so we've got 1 non-bonding pair. So electron pairs is tetrahedral, but the molecule is trigonal pyramidal. Right, SF6, sulfur has 6 electrons. We add 6 things that are attached, no charge, so we've got 12 electrons in total around the centre. Divide it by 2, we've got 6 electron pairs, and none of them are non-bonding, so both electron pairs and molecule are octahedral. Pause the video and find the shape of the electron pairs and the molecule for each of these. So for SH2 we've got 6 plus 2 things attached and no charge, so 8 electrons around the centre. Divide it by 2, so we've got 4, so electron pairs is tetrahedral. And if we take off the 2 things that are attached, we've got 2 non-bonding pairs, so the molecule itself will be angular like water. Here we have an ammonium ion, so 5 electrons on the nitrogen, plus 4 hydrogens attached, minus a charge of 1, so it's going to give 8 electrons around the centre. If we divide that by 2, we've got 4 electron pairs, tetrahedral. If we take off the 4 things attached, we've got 0 non-bonding, so your molecule is also tetrahedral. And our last one here, ICl4-, so you have 7 plus 4 things attached, minus that 1 minus charge, so that will add on. So that'll give you 12 electrons around the centre. Divide it by 2, we've got 6. So your electron pairs are octahedral. We're going to take off the 4 things that are attached, so we've got 2 non-bonding pairs, so the molecule itself will be square planar. Thank you for watching my video. I hope that you found it helpful. Please remember to subscribe and ring the bell to be notified of new videos. You can also follow me on X at miss.adams.chem, Instagram miss.adams.chemistry, and TikTok miss.adams.chem for updates on new videos, flashcards and short videos throughout the year. Bye for now.